All right, demyelination. So myelination occurs late in development, and in a lot of species, it continues postnatally. So demyelinating diseases are relatively common in animals. Just a quick review of how myelination happens. The myelin sheath around the axon is actually formed by the membrane of the cell that's myelinating the axon. So, all right, so if here's your axon, here's your myelinating cell, right? It comes up and it grabs on with its membrane, and then it just wraps. So you just have a tube of myelin and then like a little squished nucleus out here, and then that's your myelinated axon. So myelin is actually all cell membranes and cell lipids and proteins. The formation of this depends on interactions between the axon and the myelinating cell. So they're giving signals back and forth. So it's a two-way communication street. An axon can survive without its myelin. So that's primary demyelination. You lose the myelin, the axon's still there, it's okay, but conduction is slowed and you will get signs, but not from death of the axon. Axonal loss, because of these interactions that are critical for myelination, axonal loss will lead to immediate disintegration of myelin. So that's secondary demyelination. I've damaged my neuron, the axon is dead, the myelin can't survive without the axon. Demyelination is mostly a CNS problem. It does happen in the peripheral nervous system, but because of the nature of the relationship between the myelinating cells and the axon in the central versus peripheral nervous system, central is much more susceptible. So in the central nervous system, you have one oligo that is responsible for myelinating multiple axons and multiple segments of multiple axons. So it's this guy, he's spinning a lot of plates. There's one oligo and he's balancing all these axons up here. Versus the peripheral nervous system, you not only have one Schwann cell to one axon ratio, you also have multiple Schwann cells per axon. So that's this guy. He's like, I lose a Schwann cell, no big deal. I've got 20 more over here, just waiting to myelinate me, whatever. So demyelination is much more of a problem and usually much more severe and noticeable in the central nervous system because this poor guy is already overworked. One more thing is just going to push him over the edge. I relate to you, buddy. Primary demyelination. So again, this is primary myelin loss surrounding axons that are intact. The axons survive, but you get slowing of conduction, resulting in these white matter signs. It's primarily the result of damage or death of oligodendrocytes. Because their main function is myelination, this is expressed as damaged myelin. So the death of one oligo will lead to a degeneration of all the myelin sheaths supplied by that cell. So you lose this guy, you've lost multiple segments and multiple axons are being demyelinated. Some etiologies, there's quite a few things that cause this. Viral causes are very important in animals. Specifically, draw your attention to border disease in ruminants and canine distemper in dogs. There's a handful of heritable hypomyelinating or dysmyelinating diseases. We call them leukodystrophies for abnormal white matter growth. And this is usually a result of either less oligos or the oligos are immature or some way, or they're forming myelin that's abnormal structurally, so it's very fragile. You can also get immune-mediated destruction. This is how multiple sclerosis works in humans. It's immune-mediated destruction specifically of your myelin proteins and leaves your axons naked. Some nutritional and metabolic things, so some toxins, copper deficiency, classically, known as enzootic ataxia or swayback in sheep and goats. And then there's some congenital kind of generalized tremor syndromes. This is a hairy shaker. This is a normal, presumably age-matched control. And this is a lamb. His growth is stunted. His wool is hairy, and they have tremor syndrome. So this is classic border disease presentation, the hairy shaker lambs. There's another one. It's so cute. It looks like a sad little puppy. So this is, again, border disease. This is viral demyelination. So this is not an H&E, our normal stain. This is a Luxol fast blue. Don't worry about writing that down. You don't need to know that. Unless you're going to become a pathologist. But Luxol fast blue is a specific stain for myelin, and as the name implies, it stains myelin blue. So, so gray matter right here, horns, butterfly, central canal, white matter. This section up here, consider this normal white matter. Very, very, very blue. Axons will stain pink, myelin stains blue. You've lost, starting like here, like right outside this lesion, and especially bad down here in the ventral white matter tracts. You have lost so much myelin. All the white matter should look like this. It's not like this. There is no myelin in here. So this is viral damage to oligodendrocytes. Questions? Yeah.
If you have immune mediated, because you have oligodendrocytes versus Schwann cells, would the immune mediated be either central or peripheral? Or
It can be, yeah.
Yeah.
The border disease and hairy shakers the same thing or different?
Hairy shakers are border disease. Yeah. All right, secondary demyelination. This is death of the axon is the primary event, and then you get loss of trophic factors and secondary loss of myelin. So this is diseases targeting neurons, specifically axons, not oligos. Secondary demyelination is way more common in animals because there's a lot of causes. It's anything that causes axonal loss. So anything from neuronal cell death to spinal cord, specifically, it's especially common in spinal cord. Because it's a result of Wallerian degeneration, where you get compression or transection of an axon, and you lose the axon distal to the injury. My God. And as you lose this axon, the myelin that's around it disintegrates and goes away. So that is secondary demyelination. So this is super common. Lots of things cause this. Here are some this is an acute case of spinal cord compression. You appreciate here is normalish cord, here is normalish cord, and right here in the middle, it's softened, it's a little shrunken, it's kind of brown, reddish in color, not quite right. So this would be a more acute compression. Here's a more chronic, more severe compression. You actually have a little dip in the spinal cord. So both of these areas will have reduced numbers of axons, and along with that, when the axon goes away, the myelin goes away. Secondary demyelination here is an example of, well, actually, you guys tell me, what's the lesion here? What's the issue? Where are we? Spine.
Narrowing of the canal.
Narrowing of the canal. Why? Fracture. Vertebral body fracture. I'm glad you didn't say disc disease. That was the tricky thing I was hoping to get from you, because there's a space here, but here's the disc. Here's the disc where this is a fracture of a vertebral body with secondary spinal cord compression and probably some laceration. I think there's some hemorrhage there. So would this spinal lesion be acute or chronic? Acute, yes. So this will be an acute, probably very severe presentation, because that's a lot of compression. All right, secondary demyelination. This is called the digestion chamber. So these are normal myelinated axons up here, and this here is a dilated axon chain. So you've lost the axon in the middle. All of these should have an axon running through them, like so, and then you should have a little stacks of myelin around it. So that's all these guys, all this bubbly stuff, stacks of myelin. Here you've lost the axon. The axon's totally gone. These are Gitter cells. So macrophages are coming in to clean up axonal debris, and they're also eating the myelin. See the foam in there? These guys are full of myelin. So this is a digestion chamber. So it's a dilated, empty axon sheet. The axon's gone. It's full of macrophages eating their dead remains. Happy Halloween. So this is a longitudinal section of some myelinated axons. Here's more of a transverse section. And here you can see those dilated axon sheets. So let's find you a normal. The normal good. So here, this little pink spot is an axon in its little myelin sheath. Right, nice and small. You can barely pick it out. There's a little axon in a myelin sheath. All the little pink dots, axon myelin sheath. This is a massively swollen axon. So this guy is on the way out right here. These are called spheroids. Don't you love how descriptive pathology is? We just call it like we see it. There's a digestion chamber, little macrophage, eat stuff in there. So all of these big circles, these are empty axon chambers where axons used to be, now are not. All right, while we're talking about holes, spongiform encephalopathies. Quick note, we're going to talk about transmissible ones only, but there are some non-transmissible familial versions in humans. Who knows what kuru is? Trivia fact. Yeah, what is it? Cannibals. It's the cannibal disease. Don't eat people. Eating people is wrong. All right, so transmissible versions are of primary importance in animals, although familial forms are important in humans. A prion, as you guys hopefully have learned by now, is an infectious protein. So this literally means PR is protein, and this is infectious, so it means infectious protein. The prion protein is a normal protein that's actually concentrated in the brain. It's also found in lymphoid tissues. It forms a component of the neuronal cell membrane, but we don't know its normal function, but it is present in the brain. There is a misfolded variant. So the normal protein is here. You have these alpha helices, and then a misfolded version of this would occur in a beta helix, which is important because this form is poorly digestible or indigestible. This is the same thing as amyloid plaques in Alzheimer's. That form in the brain is also a beta sheet. It's not a prion, it's a beta folded protein, so it's not digestible. Other issues with the prion misfolded variant is that it is self-replicating, so it can actually cause misfolding of normal proteins that it comes into contact with, normal versions of the prion protein, and it's resistant to digestion because of this form. There are some pretty interesting host genetics of susceptibility that's been investigated in sheep. So sheep with a certain allele are more resistant to developing prion disease, where if you have another allele, you're more susceptible. And there is a incomplete species transmission barrier that's really important. So that means there is some cross between species. There is not a complete species barrier. There's a little bit of transmission, especially of the bovine form. So BSE, as you know, we worry about eating meat of, mad cows, BSE cows, because it is transmissible to humans. It causes VCJD or variant Creutzfeldt-Jakob disease in humans. So there is some species barrier between certain species and certain forms, but it is incomplete. So a lot of these, we should be concerned that they may potentially be transmissible to humans. This doesn't cause any gross lesions. There's no inflammation. So this is more of a degenerative disease presentation. And the lesion is basically spongiform encephalopathy, kind of speaks for itself. I will show you some photos and you'll be like, oh yeah, that does look like a sponge. So this is just kind of speaking to that incomplete species transmission barrier. We have detected natural transmission of specifically BSE, the cow form, to many different species, including lots of zoo species. Experimentally, even more animals are susceptible to it, and in vitro, meaning we've infected cells in cell culture from these species, and they are susceptible. The virus does replicate. So all of these are theoretically possible for transmissions. Okay, and here's the sponge. So spongiform change refers to both these large vacuoles that form in neurons. Here's a neuron right here, outlining him. Here's his nucleus, and he's got these big, it looks like a butt. He's got a big butt in his cytoplasm. And also in the neuropil, you have vacuoles. So down here, here's a neuron with a vacuole, all these little guys in the neuropil vacuoles. And then these vacuoles, once they get large enough, will cause neuronal degeneration and neuronal necrosis. So the diagnosis of this, it is post-mortem. We need to look at the brainstem and or the retropharyngeal lymph nodes. So these are the important samples for diagnosis of prion disease. Brainstem lymph nodes, retropharyngeal. And diagnosis is by histopathology and immunohistochemistry, where we actually look for the misfolded protein variant. Here's another pathognomonic lesion. A sheep brainstem with neuronal vacuoles. Pathognomonic or scrape. Here's an IHC. Brown is positive, so this is staining for the abnormal prion protein. This neuron is full of it. This neuron here with the big vacuole is full of it. It's everywhere. Oh. All right. Questions on prion disease? Regeneration, remyelination. Okay, so who this is? Nerds, what are nerds at? Yeah, this is Doctor Who. So Doctor Who has been going on for so many years that there have been so many people to play Doctor Who because the character dies and then he regenerates as another actor or actress. It's a good show, check it out. All right, so he's the king of regeneration. Determinants of regeneration in the nervous system depend on primarily these factors. So we already talked about location, oligos in the CNS. There's limited regeneration and remyelination just because they're already doing so much. Doesn't take much to push them over the edge. And your hopes of regenerating and remyelinating are low after that insult. There's also no basal lamina surrounding the axon for scaffolding, so it doesn't have anything to kind of help direct its growth if it wants to resprout. In the peripheral nervous system, Schwann cells, when you get transection of an axon and dying back of that axon, the remaining Schwann cells will actually proliferate and form a little tunnel that makes basically a perfect guide for the axon. They're like, sprout this way, and that's called a Bunger's band. Band of Bunger. Yep, so the Schwann cell wrapping creates this tunnel to guide sprouting of axon. So that actually is not just for remyelination, but that helps regeneration of neurons. You're able to regenerate more in your peripheral nervous system. And then the stage of development. So neonates, remember there's postnatal myelin development going on in a lot of species, especially in altricial species. You guys know what that word means? So altricial versus precocial, or precocious. The precocious species is like they hit the ground out of the uterus and they're up and running and ready to go. So like ruminants, horses kind of to an extent. And altricial species is the opposite. So a baby human, a baby bird, totally helpless, not fully developed. Those are the species that are still myelinating, right? That makes sense? All right, so death and degeneration. Single necrosis, usually neurons. Malacia is very common. It's death of everybody. Distribution gives you clues. Is it gray or white? Is it brain or cord? Is it symmetrical? Few pathognomonic lesions, especially salt toxicosis in pigs, primary and secondary demyelination, et cetera, et cetera. Questions?